Assalamualaikum and hi, my name is Muhammad Hakimi bin Abdullah and I will present my innovative project name IoT-Based Heavy Metal Eye Detection with Data-Driven NLP. As we know, agricultural cultivation is essential for food security, but it hides a growing environmental crisis. Modern farming relies heavily on phosphate fertilizer and also a cocoa-based fungicide, which has invisible environmental traces like copper, cadmium, and zinc. So here I introduce our project, IoT-based heavy metal ion detection with data-driven NLT. You can scan test strip using TCF3200, process using ESP8266, as well as transmit data heavy metal to cloud, which is ThinkSpeed. Give real-time dashboard as well as contamination status equipped with alert for early warning contamination. But wait, why do they just rely on standard laboratory testing? Technology like ICP-MS are incredibly accurate in details. Laboratory measurements, while precise, have a critical flaw, which high operational time and high cost. So by the time sample collected from a rural canal sent to the lab and analyzed, the toxic pump has already happened. So in this case, lab precision is ineffective if it arrives too late. You may ask, if it's the main problem of the laboratory testing, it takes too long and costs too much, why don't we just use commercial color test strips? Just deep, look into the color, and immediately know if heavy metal are there. Why do we need entire IoT enclosure, sensor, and cloud algorithm? This is a fair question, but relying on the human eye and basic test strip create two massive failures. Subjective human eye, where can be easily fooled by ambient sunlight, and lack of predictive foresight, where test strip only tell you what is happening right now. In not the data, it cannot alert the upstream authority, and it cannot predict the future.
First, we dip our test strip into sample water. We turn on our hotspot before start scan. After that, we turn on our switch and green LED will light up. As you can see, the LED blink is the countdown before it scans to give time to move test strip. As it scans, the LED stays on as it reads and continue to count down until it finishes scan all at heavy metal. Then we proceed to dashboard and it shows it successfully uploaded and it gives not only graph for add heavy metals, it also shows status for actual contamination and predicted contaminations. As for early warning, it will alert if threshold achieved more than 0.7. And for this demonstration, it will show the email alert and yep, we received.
This prototype serves as an intellectual optimization challenge. The chamber not only house of sensor but also regulate the Beer-Lambert law to minimize light scattering and ambient distortion. Its interior is lined with a black material and use a constant white LED source. This design ensures that change in the RGB frequency matrices are solely due to chemical concentration on the paper matrix, providing consistent data reproducibility in varying outdoor conditions. The novelty of our project lies in the data analytics. Unlike traditional water sensors that use basic threshold alert, our analysis allows that agriculture heavy metal runoff behave as a correlated classified sum. For example, we found a strong correlation R equal to 0.79 within the lead and cadmium due to their presence in commercial phosphate fertilizer, supporting our multi-variable approach. We also developed novel temporal features like random forest classifier, on the cloud backend to harness hydrostatic method. By structuring historical time series data with a look-ahead target vector, our model predict multi-metal breakthrough through an optimized lead time of 4 days at 80% accuracy. This advancement transformed the system from a passive observer into an intelligent forecasting tool. Our project focused on two main UN Sustainable Development Goals, specifically SDG 6 for clean water and sanitation. It emphasized that prevention is better than cure. Current water management often react only after contamination occurs, leading to an intensive damage and requiring costly remediations. Another one is SDG 40 for life below water, and we know General River is a home for fish. Fish focus on preventing and significantly reducing marine and freshwater pollution of all kinds, particularly from any harm, specifically heavy metal. Let's talk about potential and business perspective. To access the scalability of our project, we examine the architecture of our prototype. It utilized low-cost micro-components, resulting in a production cost more lower than commercial spectratory systems. This affordability allows for potential mass development and distribution mass network across numerous rural drainage and get small to medium industrial discharge channels. This communication layer uses standardized HTTP protocols through the non-MCU ESE8266 to push data to a centralized cloud architecture with automated ingestion latency under 5 seconds. It output the time series JSON data, allowing easy integration into existing smart city environmental monitoring framework or industrial system via API webhooks without proprietary change. The system's social value application relies on a predictive lead time with 80% forecasted accuracy. This window allows municipal authority to proactively close the water intake valves and enable agriculture officers to divert a supply into a retention basin. By shifting from reactive disaster response to a proactive safety approach, this prototype provides a practical blueprint for safeguarding public health and river ecosystem. In conclusion, this project redefined environmental protection by shifting from reactive crisis response to an intelligent preventative shield. By combining a zero flow base with a temporary machining engine, we achieve a validated 4 days warning window at 80% accuracy before agriculture heavy metal runoff can compromise public water. Last word from me, we don't clean the water, we intercept the pollution. Thank you.